Good day everyone. So for today's video, I will be discussing about applications of integration. In this topic, under this topic is we have area and polar area, and we're also gonna be discussing about volumes using integration. So without further ado, let's start. So in area, we have um, area under the curve, and we have area between two curves. Now let's start with area under the curve, or shall we say a line. So area under the curve. Now let's say we have a graph here. So this is our y and x, and we have a line, something like this. Let's label this as y is equals to f of x. And we have our, let's put a and b here, points. And our area of interest is here. Now, in area under the curve, let's, to solve the area of interest, let's first put a strip. Let's say, let's label this point as x and y. Put a point, then a vertical strip. So the width of the vertical strip, let's label this as dx. This is dx. And this is our x. And the height of the vertical strip is our y. Now if we take this out, this is our dx and this is our y, right? Now if we solve for our differential area, this is just gonna be y times dx. Now if we integrate both sides, the d here will cancel, and the integral of y dx with limits from a to b. So this is actually the concept of area under the curve. Now let me give you an example. Let me erase this first. So remember that always label, so that we know, always plot the graph and label so that we know how to get the area. Now let me give you an example. So remember this. Now example number 1. Let's say find the area under the curve. Let's say find the area under the curve y is equals to square root of x from x is equals to 0 to x is equals to 4. Now our solution here is, first we need to graph. So let's say our graph is, this is y, this is x, and actually y is equals to square root of x here is just a curve like this. So let's label this as y is equals to square root of x. And our limit here is 0 to 4, right? So from the origin, and let's say this is our 4 in here. So this is our area of interest. Now if we put a vertical strip here, let's say a point, this is x and y, draw a vertical strip. This is dx, the width of the vertical strip, and we have the x, our x, and of course the height of the vertical strip, which is y. Now if we take this out, let's say our vertical strip, this is dx and this is y, right? So to solve for the differential area, we have y dx. So integrate both sides, we have area is equals to integral of y dx. So the area now is, our limits here is 0 to 4, right? 0 to 4. And our y is square root of x. Or we can just write this as x is equals raised to 1/2, right? dx. And now if we integrate this, this is just x. This is 1/2 plus 1 is just 3/2 over 3/2 with limits from 0 to 4, right? Now if we distribute if we distribute the limits, this is just let's say 2/3 x 4 raised to 3/2 is just 8, right? Yeah, this is 8 minus, so if you plug in 0 here, this will just become 0. Now our final answer here, let's put our final answer here. Our final answer, area is equals to 16 over 8 times 2, 16 over 3, and our unit, which is square units. Now this is our answer. This is the process on how to solve or how to find the area under the curve. Now let me give you another problem. This is let me see. Let's say we have a line. So example number 2. Let's say find the area under the line y is equals to 3x plus 3 from x is equals to 0 to x is equals to 5. Now so our solution here is of course plot the graph. Now how do we solve this, or how do we get its points? Now let's say we have x and y here. Now if our x is 0, so if our x is 0, this is just 3. And if our let's say if our x is 1, this is just 3 plus 3 is equals to 6. Now if we plot it in the graph, let's say this is our graph, this is y, this is x, and this is 0. So if our x is 0, y is 3. So somewhere here. And if our x is 1, let's say somewhere here, our y is 6. Let me put 1 here so that our line is passing. And this is here, right? let's say from here to here. Oh, sorry. Supposing this is a straight line, and of course our limit is 0 to 5, so let's just say this is 5, right? So our area of interest is here. Now after that, let's say we have a point here, x and y, and we'll draw a vertical strip. This is our vertical strip label. This is our dx, and this is our x. Of course, this is our y, the height of the vertical strip. Now, if we take this out, the vertical strip, we have dx and y, right? So, to solve the differential area, is just y dx. Now, if we integrate both sides, we have area is equals to the integral of y dx. Now, area now is just, so our limits is 0 to 5, and our y here is 3x plus 3, right? Now, integrating, we have 3x squared over 2 plus 3x with limits from 0 to 5, right? Now, let me put it in here. Now, this is just 3 halves. So now, substitute the limit. We have 5. Let's say 5, or let's say 25. Because 5 raised to 2 is 25. Plus 3 times 5. Now, if we substitute 0, it will just gonna be 0. So, we will not write that. So, this is just, so 25 times 3 is 75 over 2, plus 15 is 105 over 2. So, our answer here is, let me erase this. So, our answer here is 105 over 2 square units. This is our final answer. So I guess that's it for area under the curve. Now let's go to area between two curves, or shall we say area between two lines, or a line and a curve, right? So let's go to area between two curves. Supposing we have a graph here. This is y, this is x. And we have a line passing through something like this. Supposing this is a straight line. And we have a curve passing through the line. Okay? Now let's label this as y is equals to f of x and y. Let's say y, this is y1 and y2 is equals to f of x sub 2 sub 1. So our area of interest is somewhere here. And of course, this is our intersection. This is A, and this is B. Now, if we put a point here, let's draw a vertical strip. Let's label this point as x and y. This is our vertical strip, and then of course the thickness of our vertical strip is dx, and our y, our x rather, And the distance of the upper to the x-axis is just y squared, right? I mean y, this is y1, since the line is passing through the curve is in the y1, so we label this as y1. Now, here, this is x sub 2, y sub 2, right? Now, the point here, let's say, okay, we label this as y2 since our line here is y2. Now, if we take this strip, vertical strip, this is just gonna be, so this is our dx, and this is y1, so our upper part here, this is y1 minus the lower part. So basically, the area here is just y1 minus y2. The area is y1 minus y2. Now, if we take, if we get the differential area, this is just y1, y sub 1 minus y sub 2 dx. And of course, if we integrate both sides, this is just the integral of the limits from a to b, y1 minus y2 dx. So this is our formula in solving for the area between two curves. Now let me give you an example. So example number 1. Now I will give you a graph and then let's find the area. Let's say we are given a graph. Let's say a parabola opening upward. So this is just y is equals to x squared. So x squared is just a parabola opening upward. And we have a line here. Let's say we have a line. This is y is equals to x. Let's label this as y parabola and y line. So our area of interest is here. So this is our points and this is our point. And this is actually labeled as 1, 1, and this is 0, right? Now, let me draw a vertical strip. So supposingly this is our vertical strip, and the thickness of the vertical strip is dx, and the distance of the vertical strip to the y is x. So now, labeling is very important. Now, if the point here is, since this is along the x-axis, the line, let's label this as YL. And this point, let's label this as YP, since it is along our parabola. So the area here is just YL minus YP. So now if we take this out, let's put it here. So this is just dx and YL minus YP, right? Now if we take the differential area, this is just YL minus YP. Now if we integrate both sides, this is just the area is equals to the integral with limits from, let's put our limits, we have 0 and 1. 0 and 1. And our y line here is x and minus x squared, our y parabola. And don't forget to add dx. This should be dx also. Now if we integrate, we have, let's say, let's put it here. Area is x squared over 2 minus x cubed over 3 with limits from 0 to 1. And now this is just, let's distribute the limits. We have 1 raised to 2 over 2 minus 1 raised to 3 over 3. And if we distribute the 0 here, it will just gonna be 0. Now this is just 1/3, let's say 1/2 minus 1/3. Now if we minus this is just 1/6. So the answer here is 1/6 square units. So that's how you solve or find the area between two curves. Now let me give you another example. Let me erase this first. So let me give you another example. Example number 2. So what if we are given a graph like this? So this is y and this is x. And let's say we have a curve here labeled as x is equals to y cubed, and another curve, this is x is equals to y squared. Now let's label this as x sub 1 and x sub 2. Now our area of interest here is here, and then if we draw a vertical strip, this is just dx and our x, and of course our height, the height of our vertical strip, which is y. So now oh okay, let me give you, let's solve this problem. Let's use horizontal strip. Let me erase this. So you can use, by the way, you can use horizontal or vertical strip depending on the problem. Now let me, let's say this is our point and our point here. This is our, supposedly this is our vertical strip. And of course, if I mean horizontal strip, so this is our dy since it's along the y-axis, and let's say the distance of our curve here from the y is, let's label this as x sub 1, and the distance of our curve here from the y-axis is x sub 2. This is x. So the area here is just x sub 2 minus x sub 1, the area here at the center. Now let's take this out. So this is just dy and x squared minus, I mean x sub 2 minus x sub 1, right? Now if we find the differential area, this is just x dy, since it's x, and then the differential, if we integrate both sides, this is just area, is equals to the integral. Let's say our limits here is 0 to 1. So 0 to 1. And then our value of x sub 2 is what? Y squared minus y cubed dy with respect to dy. Now if we integrate, this is just let me put it in here. This is just y cubed over 3 minus y raised to 4 over 4 with limits from 0 to 1. Now if we substitute the values of the limits, we have 1 third minus 1 raised to 4 over 4. And if we substitute 0 is, it will just gonna be 0. So now our area is, this is just 1/3 minus 1/4. So this is just 1/12, right? Square units. So this is our answer. Now I guess this is just a simple way to find the area between two curves. Now let's go to our next topic, polar areas. So let's say let me erase first. So our next topic is polar areas. Now let's say we have, so let's draw a graph first. Let's say we have something like this. And then we have this is our area of interest. Now in solving for polar curves or areas, this is just, let's say let's put a strip here going up. This is, so this is just r radius and radius, right? Since let's say this is a circle divided into different parts. Let me do that again. And then the part, let's say this is our area of interest. So basically this is just one part here is called a sector, right? This is sector. Now this is radius and radius, right? Now the area of the sector is just 1/2 r squared theta. So this is in radians. Now going back here, this is just d theta, and of course the radius and radius. Now if we find the differential area, this is just 1/2 r squared d theta. And if we integrate both sides, this is just area is equals to 1/2 r squared, let's say with limits to pi over 1 and pi over 2. Let's label this as pi over 1 and pi over 2. Pi 2, pi 1, 1/2 r squared d theta. So this is actually the concept behind the polar curves, or let's say formula in solving for the polar areas. Now let me give you an example. So let's say we have example number one. Let's say we have find the area of r is equals to 4 sine theta. Now for if in order to plot the graph, we need to find our points, right? So let's say pi and r, let's say 0 degrees, 30 degrees, 60 degrees, 90, 120, 150, say 150. Let's do another one. 180 degrees, and then 210 degrees, 240, 270, 300, 330, and 360. Now to find uh the radius of the angle here, or the theta, let me solve using the calculator, so that it's easy for us to find it. Now let's say we have um, first is our mode should be in degrees. So I mean, let's and then let's choose table here 7, and then our function is 4 sine. So 4 sine. So instead of theta, let's put x, or there we go. So our starting point is 0, right? And our end is 360. And our we skip by 30, right? So 30. Now this is uh, our radius. Now if we have 0, our r is also 0, right? So this 0, this is 0 now, and if 30, this is 2, 60, we have 3.46, and then 90 is 4, 3.46, 120, and then 2, and then 180 is basically, this is 0, then negative 2, negative 3.46, then we have negative 4, negative 3.46, 330 is negative 2, and 0. Now we can plot the area. So let me just erase this so that we have space for our graph. I already take this down, and I noted down, and I will just put the graph. Let's say our graph is like this, and of course, since our highest radius is 4, so this is just r1, r2, r1, r2. Supposing this is a perfect circle. Then we have R4. Now, after that, we label the angle, or let's say degrees. So this is 0 degrees, this is 90, 180, and then 270, right? This is 30, 60, this is 120, this is 150, this is 210, 240, this is 300 degrees, 330, and of course 360. Now if we plot the our area, so if our our area, let's say if 0 degrees, our radius is in 0, right? So here, if 30, so our radius is 2. If 60, our radius is 3.46, so somewhere in here. When 90, our radius is 4. When 120, our radius is 3.46, so somewhere in here. When 150, our radius is 2. When 180, our radius is 0. When 210, our radius is negative 2. So, if this is 2, negative 2 is just the opposite, or the, so the opposite, so this is just in here, right? If 240, 3.46, the opposite. 270 is just 4, negative 4, this is just the opposite. And 300, we have negative 3.46, the opposite. So here, and then 330, this is just negative 2, so the opposite is in here. And 360 is just 0. So our this is actually a circle. Supposing this is a circle. Now, if if we need to find this area, what do? So first is draw a strip here. So this is R and R, right? And of course our d theta. I hope that it's clear. So now, if we take this out, this is just somewhat like this, right? This is d theta. Now, if in order to find this is just the differential area of 1/2 r squared d theta, right? Now, if we integrate both sides, this is just the integral. Since this our area is within this section, so this is our limit here is just 0, from 0 to 90. 90 here is pi over 2. Since pi is 180, over 2 is 90. So our limit here is 0 to pi over 2. 1/2 r squared. So r squared, if we square this is just 4 sine a theta squared, right? D theta. Sorry, it's, let me rewrite this. So area is just the integral of 0 to pi over 2 with limits from 0 to pi over 2, 1/2 4 sine theta squared d theta, right? Now if we put the 1/2 outside of the integral, oh, uh, uh, this is you need to know something, that if you, this is just a part of the circle. Now if we uh, uh, find the whole area, this is just the total area. Let's say total area is equals to, so we need to multiply this by 2. So this is just 0 to pi over 2, 1/2 4 sine theta squared d theta. Right? Let me erase this so that I have a space. Sorry about that. So a total is just the 2 and 1/2 here will cancel. So what's left is it's just 0 to pi over 2 integral of, with limits from 0 to pi over 2. This is just 16 sine squared theta d theta, right? And then if let's solve this using a calculator. Okay, so let me show you. So let's comp, press 1, and then we have in solving this you need to have in, you need to have it in red. So now integral with limits from 0 to pi over 2, let's say 16 sine, so instead of theta let's put x, oh sorry, squared, right? So equals, so the answer is 4 pi square units. So this is our answer. Now let me give you another example. So let me erase this. Example number 2. Let's say find the area of r is equals to 2 minus 2 sine theta. So of course we need to plot the graph. So we need to find the points. So let me draw the graph, since I will just list down the points. So the radius is, our highest radius is 4. So let's draw 4 circles. So let's say this is radius 1, radius 2, radius 3, and radius 4. So this is 0 degrees, 90, we have 180, we have 270. So according to the problem, we need to plot the points. Now if when our theta is 0, so the r, our radius is 2. So in here, right? Oh, let me, so this is 30, 60. This is 120, 150, This is 210, 240, 270. This is 3, 300, 330, and of course 360. Now, if we when zero, when our theta is 0, our radius is 2. When it is in 30, this is just 1. 60 is 0.27, so somewhere here. And 90 is 0. 120 is 0.27, so somewhere here. 150 is 1. 180 is 2. 210 is 3. 240 is 3.73, somewhere here. And then 270 is 4. 3.73 is 3 in 300. 330 is 3. And of course 360 is also 2. Now our it should look like this. Now if we find the area of this part, so of course if you find half of the whole area, you need to multiply it by 2. So let's say we have a strip here. Uh, let me draw. Let's say we have a strip here. This is R, and we have d theta. So let me erase this part so that we have some space. Now let me draw this. It should look like something like this. So this is R, and this is d theta, right? Now to find the area of this is just the differential area is equals to 1/2 r squared d theta, right? Now if we integrate if we integrate both sides, this is just the integral of, so since we to find our limits, this is just from 90 to 270, right? So 90 is pi over 2, so that is our limit, and 270 is just let's say this is just 3 pi over 2. And of course, don't forget to add or multiply rather 2, since this is just the part of the area that we cover. So let's label this as A total, and 1/2 our r squared is 2 minus 2 sine theta squared d theta, right? And then now we can cancel this, so what remains is pi over 2, 3 pi over 2. So this is just 4. Okay, so let me solve this using calculator. So let's solve this using calculator. So this is just the integral with limits, let's say pi over 2, and our upper limit is just 3 sorry 3 pi over 2, and then we have 2 minus 2 sine Instead of x, instead of theta, let's put x. Sorry about that. Squared. So our answer is 6 pi. So a total is just 6 pi square units. So this is our answer. Now I think that's it for the polar areas. Now let's go to volumes. Now in volumes we have three methods on how to find the volume using integration. Now let's say volume. So in volume we have three methods. The first one is disk method. The second one is shell method. And the last or the third is washer method. Now first is let's talk about the disk method. So this is disk method. Okay, so let's say we have a graph here. Let's label this as y and x. And we have a curve that's something like this. Let's label this as y is equals to f of x. And then, of course, our area of interest, this is from A to B. So this is our area of interest. Now if we draw a vertical strip, so this is just, this is our x and this is dx, right? Now, if our area of rotation is along the x-axis, this will also rotate, right? So this will rotate and it will look something like a disc, right? Let me put it in here. So something like this. Something like a disc, right? Now, this is our dx, right? So dx. And of course, our area of rotation, this is area of rotation. And of course, this is our y, the height of our disk. Now, we need to find the differential volume. This is just pi y squared dx. So if we integrate both sides, this is just the volume is equals to the integral with limits from a to b pi y squared dx. So this is the concept behind this method. Okay, so now let me give you an example. example number 1. Supposing we have to determine the volume if the area under the line is equals to y is equals to x from x is equals to 0 to x is equals to 5 rotated about the x-axis. Now, of course, our solution is first to graph. So our line y is equals to x is just something like this, right? Y is equals to x, and of course our limit is 0 to, let's say this is 5. So our area of interest is here. Now if you put a vertical strip, so this is just dx, and of course our x, and the height of this is y, the height of our vertical strip. And of course it says that it rotates about the x-axis. So this is our area of rotation. Now if we rotate this, it will look something like a disc, right? So now if we need to find the differential volume, this is just pi y squared dx is equals to, if we integrate both sides, this is just volume is equals to the integral with limits from 0 to 5. So here is our limits, y squared. So this is just, since our y is x, so if we square the x, this is just x squared dx. Oh, and don't forget, I forgot the pi, x squared dx. Now this is just, if we integrate this, this is just pi multiplied by x cubed over 3 with limits from 0 to 5, right? So if we, this is just, if we distribute the limits, so this is just 5 raised to 3, which is 125 over 3, right? So our answer here is 125 pi, or let's say pi times 125 over 3 square units. I mean, since we are dealing with volume, this is actually cubic units. My bad. So this is our answer. Now, let me give you another example. So example number 2. So determine the volume of the area under the curve y is equals to e raised to x from x is equals to 0 to x is equals to 2 rotated about the x-axis. Now, of course, our solution is, of course, first is plot the graph. Y and then x. So, basically, EX here is just a curve, let's say, a curve something like this, going upward. So, it says here our limit is 0 and 2. Supposingly, this is 2. So our area of interest is here. And then, of course, we need to draw a vertical strip. So of course, this is our dx, the width of the vertical strip, and of course our x and our y. And it says here that it rotated about the x-axis. So if we rotate this, it will look something like this, right? So this area is actually the differential volume. Now if we solve for the differential volume, again, this is just pi y squared dx, right? Integrate both sides. This is just the integral. Volume is equals to the integral. So our limits here is 0 to 2 pi, and our y squared, and our y here is e raised to x, right? So this is just e raised to x squared dx. Now let me solve this using a calculator. So let's say integral with limits from 0 to 2 pi, and then multiplied by e my bad, e raised to x, say x, then squared. So our final answer here is, so the volume is 84,1918 cubic units. So this is our answer. So this is our answer. Now let's go to shell method. So now let's tackle about shell method. So in shell method, our area of rotation is parallel to your strip. Now in this method, the strip is perpendicular to our area of rotation, right? Now in shell method, area of rotation is parallel to our strip. Now let me uh, discuss the concept of shell method. Let's say we have a graph. This is y and this is x. And let's say we have a curve here. This is y is equals to function of x from A to B, and our area of interest is here. Now if our area of rotation is in y-axis, and let's draw a vertical strip. So in shell method, the vertical strip and the area of rotation is parallel to each other. So this is dx and this is x, right? Now if we rotate this, let's say if we rotate, it will look something like a tin can, right? A cylindrical tin can. Let's label this as x and y. And if we take this out, let's say we take this out, this is something like this, right? This is actually dx. This is our y, right? This is our vertical strip, and our area of rotation, and this is actually our x. Now if we spread it, if we cut this, it will look something like a rectangle, right? So in top, this is just 2 pi x, and of course this is just y, and of course don't forget the dx, and this is our differential volume. So now we can formulate our equation. So dv is just 2 pi x. So this is just multiply, then multiply by y, then multiply dx. Now if we integrate both sides, this is just so it will gonna be 2 volume, since our d will cancel with the integral from limits to a and b. So this is our formula in solving or finding the area of uh, our curve using shell method, right? Now let me give you an example. So in shell method and in washer method, I will give you just one example. This is just a basic example. So I hope that you understand how to plot the graph, and how to and what is the concept of these methods. Now let's say we have example number 1. Let's say we have y is equals to 1 minus x, and the graph, this is y, this is x, and this is 1. Let's say we're given a graph like this. So our area of interest, and of course let's draw the vertical strip. So this is dx, right? And of course this is our x and y, with our area of rotation is along the our area of rotation is along the y-axis, right? So if we rotate this, it will look like this, right? So this is 1 and 1, 0. Now if we cut this in half, let me draw that again. So if we cut this in half, it will look something like this. So as I said, this is 2 pi x, and this is y, and of course the thickness is dx. And of course this is our differential volume. Now to solve for differential volume, this is just 2 pi x times y dx, right? And if we integrate both sides, this is just the integral with limits from 0 to 1, 2 pi x, and our y here is 1 minus x, right? Dx. Now if we take out the 2 pi outside, Now, and integrate this, or rather, let's say distribute the x first, 0 to 1. So this is just x minus x squared, right? Dx. Now, this is just 2 pi x squared over 2 minus x cubed over 3, right? With limits from 0 to 1. Now, let me put it in here. So the answer now is 2 pi. This is just, if we put the limits, this is just 1 squared over 2 minus 1 raised to 3 over 3. And if we distribute the lower limit, this is just going to be 0. So, this is just 2 pi 1/2 minus 1/3, right? And of course, um, this is just 1 over 6, right? Since we have 2 here, 2 and 6 will cancel out, and what's left is 1/3 pi cubic units. Now, this is the answer. Now I guess that's it for our shell method. Since I don't have time left, let me give you a practice problem, some practice problem in shell method. So let's now go to washer method. So washer method. So what is this washer method? Let's say if we have a graph in here, this is y, this is x, and our area of rotation is somewhere here. This is area of rotation. Let's label this as b, and this is y is equals to b. And we have the area, something like this. Something like this. So since this is our area of rotation, let me draw a strip in here. So this is just a dx, right? Let me put it in here. This is dx. This is our x. And of course our height, the height of the vertical strip. Our point here, let's label this as x and y. And the distance of the area of rotation from the x-axis is b. Now since our area of rotation is in here, we need to rotate like this, right? Now if we rotate this, so this is just something like, and of course something like this. Let me erase this. So this is just something like this. So as you can see, this is just a disc method with a hole in the inside, right? Now let me rewrite it in here. So this is just a disc method with a hole in the inside, right? And our uh, axis of rotation is at the center. So the the inner circle, this is just b minus y. And the big circle is just y, right? Now, if we take the differential volume, this is just pi b squared. This is actually not y but b. This is b squared dx minus pi b minus y squared dx, right? Now, if we take the integral, this is just volume with limits. This is actually a to b. So with limits from a to b. So if we factor out our pi here, this is just b squared minus b minus y squared dx, right? So this is actually the concept or the principles of shell method. Now, let me give you one example in this. I mean, this is washer method. Sorry, this is washer method. Now, let's say we have a problem like this. Let's say we have a parabola here, opening upward. Let's label this as y is equals to x squared. And then we have a curve here, like this. This is actually y, x. Y is equals to square root of x. Now, of course, our area of interest is here. Now, if we draw a vertical strip, let me do that again. So this is our vertical strip, and of course this is dx and our x, and this is actually y. Let's label this as y sub 1. This is actually y sub 1, and the height of this curve to the x-axis is actually y sub 2. And of course, our area of rotation is in or along the x-axis, since in washer method our strip is supposed to be vertical. Oh wait, this is correct, right? Oh yes. So let's draw the let's now rotate our area. So this is just something like this, right? Now if we take this out, it will look something like let's draw in here. It will look like something like this. right? This is our area of rotation. And this is our y1, right? y1 here. And the bigger circle is our y2. Now, to solve for, and don't forget this is our dx. I almost forgot it. Now, if we solve for the differential volume, okay, so I think, let me erase this now. So I think this is okay. Now, if we solve for our differential volume, this is just pi y squared, let's say y squared y2 squared dx minus pi y sub 1 squared dx. Now, if we integrate both sides, this is just, our limit there is 0 to 1. So, if we factor out pi, this is just y sub 2 squared minus y sub 1 squared dx. So, our so now this is just our y sub 2 is, let's say, x raised to 1 half, since our y sub 2 is square root of x minus our by the way, if there is a square, this is just gonna be x, right? So this is just x minus our y sub 1 is x squared, so x squared raised to 2 is x raised to 4 dx. Now this is just pi, this is just x squared minus 2 over 2 minus x raised to 5 over 5 with limits from 0 to 1. So this is actually pi. If we distribute the limits, we have 1 squared over 2 minus 1 raised to 5 over 5. And if we distribute the 0 here, if we distribute 0 to our equation, it will just gonna be 0. So this is actually 1 half minus 1/5. So this is actually 3 over 10, right? 3 over 10 multiplied by pi square units. So this is our answer to the problem. Now I think that's all for today now, and I hope that you have learned something, and I'll see you in my next video. Thank you.